Hello, everyone. So, our this lecture is about carbohydrates. I'm hoping that you have covered the carbohydrates general introduction, for which I have shared the link with you, and it was about the importance and its sources and what the carbohydrates do and provide for our body system. So, our this lecture is about the carbohydrates and more towards its chemistry. So we will discuss the classification and we will talk about the monosaccharides specifically. Then we will discuss D and L configuration and Epimers. These are the terminologies when you are discussing and you are starting the biochemistry and you are talking into the carbohydrates. So I hope from this lecture you will be able to understand it in a very comprehensive and in a very easy way that what are the epimers and how we can assign the D and L configuration to a specific carbohydrate. So let's start. So by definition, the carbohydrates they are also alternatively termed as saccharides, which has abbreviated or extracted from the Greek language saccharon, and it means sugar, because most of the carbohydrates are sweet in taste. So that's why they were named as a saccharon, and later they were termed as a saccharides. So they are the most abundant biological molecules. So and specifically when we are talking about the biological molecules, we are talk about the proteins, lipids, fats, and carbohydrates. So among all of these, the carbohydrates are the most abundant one. They are the very good energy source, so they don't have that contribution like the protein in our body structure or in a makeup, but they provide a lot of energy for our body system as a human. But otherwise, for if you just see at the plant kingdom, so this they are making the major um, structural feature, and the cellulose is major structural part of the plants. So chemically, if we define that what is chemically their structure and how we can define that this kind of compound is a carbohydrate, so they are basically polyhydroxyl derivatives of aldehyde. So, and ketone. So what does it mean? That it means there are more than one hydroxyl group present in the compound, and the major functionality in that compound is either aldehyde and the ketone. This is not the case that a single compound is having the aldehyde and ketone both. So they will be either the aldehydic or the ketonic one, but they are the polyfunctional because they have the extra functionality of the hydroxyl one, and this is more than one. So they are basically simpler if you just compare with the nucleotides or amino acids in structure, and they are only constitute of the three elements. So they are the carbon, hydrogen, and oxygen. So basically they are some of the derivatives of carbohydrates, which we will talk about talk later, but they are the terms as derivatives. This is not the main structure of the carbohydrate. So when we're talking about the main or the basic carbohydrates, so they are just consist of three elements. This is the carbon, hydrogen, and oxygen. And they are mostly combined in a ratio, which is just like a water ratio, uh, 2:1. So in this, the carbon and oxygen is in a ratio 1, and the hydrogen is in ratio 2, as like the water. So if you just I want to write its generic formula for the most of the simpler carbohydrates, that in what ratio the hydrogen, oxygen, and carbon are present. So this is a CnH2, H2n, and ON. So it means N is basically the number of carbon. So how many the carbons are. So there will be equivalent oxygen, but the double of this is the hydrogen. So though there are some of the exceptions are also there, but largely they exist in that ratio. So you know the glucose formula and this is the C6H12O6. So oxygen and carbon have the same ratio or the same number of the atoms, but the hydrogen is just a double of it. So another important point is that this N doesn't start from the one. So this is the for the carbohydrate, because there is one functionality is either aldehyde and ketonic one, and secondly they are the polyhydroxyl group. So it means the carbon is not enough, that it is only have the only one carbon structure cannot be the carbohydrate one. So there is a minimum number of carbons present in the simpler carbohydrate is the three. So it starts from the three onward. So they are the number of and a very high number of the carbons which could be the part of that carbohydrates. So we will talk about their complex structures and how they are combining with one another. So by definition, you can state that these are the polyhydroxy derivatives of aldehyde and ketone. Now the classification. So how the carbohydrates are classified. So they are basically classified on the basis of their complexity and the specialization in terms that how many different monosaccharide units are combined. As we discussed in the proteins, so they are the more than 2, 3, 4, and up to 100 different amino acids combined to make the protein structure. So likewise, carbohydrates do combine with each another to make the more complex and more higher structure structure of that carbohydrates. So on that basis, that how many units of a basic carbohydrate structure are combined, so they have classified on the basis of that. So the carbohydrates can be classified as a monosaccharides, oligosaccharides, and the polysaccharides. So in most of the literature, you may seem they don't mention the oligosaccharide. They can directly go to the monosaccharide, disaccharides, and then the polysaccharide. So I will define you that what the monosaccharide is. So monosaccharide is the basic unit or basic structural uh, the basic structure of carbohydrate. So you can say the unit cell, which we talk about the crystals of our organic compounds. And this is again the organic compound is that which is just the first part, which is was the smallest part, right? So which is giving you the all features of that carbohydrate, but this is the smallest unit. So that is termed as monosaccharide. So by combining the different monosaccharides, we can get the disaccharides and then the oligosaccharides. So monosaccharide is only the one unit which is just making the one saccharide or one carbohydrate and its complete structure, and this cannot be break or hydrolyzed into the further monosaccharide units. So this is just like an example of an atom. So atom is indivisible. So an element is basically the basic structure, but by the combination of the same element or the different elements, they are making the compounds and the molecules. So monosaccharide is a single or the basic structural feature of the carbohydrate. So these are the examples of a monosaccharide. So this is basically the 6 carbon structure, and this is mentioned in the style which is termed as the Fischer projection, in which we are mentioning that this hydrogen is on the left side, this hydroxyl is on the right side, this is on the left side, and this is on the right side. So in the glucose, this is the structure of the glucose, so which is our constitute the major of our food component. And in our metabolic cycles, we compose the carbohydrates and simplify into the simpler um, um, carbohydrate units in the monosaccharides, and the most basic one is the glucose. And this glucose then converted into the carbon dioxide and the water plus the amount of energy by which we are able to perform our different physical activities. So this is a 6 member, 6 carbon structure, and this is a glucose in its open structure form. And if we are mentioning that which group is at the right side, which group at the left side, so this is called the Fischer projection, and this is its open structure. But when they are going towards a more complex structure, so these carbohydrates do exist as the cyclic structures, right? So we will see that under what conditions that cycle can be formed. So they actually, this compound chemically has the hydroxyl group. This has this aldehydic functionality. So they go through the intermolecular cyclization. So that's why when the aldehyde combined with the hydroxyl side, so they make the acetals. So due to this acetal formation, they cyclize, and this is more easier and more compact and more stable form for that glucose. So they can adjust the number of different monosaccharide units to make the very high structures. As one example is the cellulose in our body system. The extra carbohydrate is stored as glycogen in plant. This is stored as a starch. So they are um, they have the number of or more than 10 and 20 monosaccharides in their structures. So this is the more compact form and the stable form. So that's why they can easily cyclize in their structure, and they do exist in nature in that form. So now the oligosaccharide is the second way in which uh, the carbohydrates, which are made up of uh, the different monosaccharide units, by combining these, and they may contain from 2 to 20 up to 20 monosaccharides if they are combined to make a carbohydrate or the saccharide. So that has termed under the oligosaccharides. So from the oligosaccharides, we can separate the disaccharide separately. And why we are emphasizing on it, it is because the disaccharides are most abundant oligosaccharides in the nature which do exist. For the example is the sucrose, maltose, lactose. So they are by the combination of the two monosaccharide units. So usually the most of the carbohydrate do exist as a disaccharides, but they are the polysaccharides as well. So in oligosaccharides, the disaccharide rather than the tri and the tetra saccharides, the disaccharide is more abundant one. So that's why we specifically focus this also and elaborate about this. So we will discuss some of the disaccharides as well, which are the very important and common one. Now the next one is the polysaccharides. So polysaccharide means that this is beyond the 20 monosaccharide units. So they are the carbohydrates which are more made up of more than 20 monosaccharide units. So they have n numbers. So that could be the 21, that could be 25, 30, 33, up to 50, 40. So these are the polysaccharides. And the example is starch, glycogen, cellulose. So we will talk about the polysaccharides in our next lectures as well. Now, I have showed you in this slide, there I have given you the structures of the different, one is a monosaccharide, another one is a disaccharide example, and the third one is the oligosaccharides with the 3 monosaccharide units. So this is written in a more chemistry form, but usually in your biochemistry books, textbooks, you may see that kind of structure. And there is a reason, there is a good reason for writing in this Fischer projection, because this is giving about information about the stereochemistry of that one. Because now this is not the simple structure in a way that the both are the hydrogen, then that was fine. But because they are the hydroxyl, and by changing this position, you can go another kind of carbohydrate. So that's why this is important, that you mention clearly and you write the carbohydrate if you are writing in their open structure. So you should go for the Fischer projection, but otherwise you know that that can be written. So this is in a horizontal form, or you can write in its vertical form in the Fischer projection. So right now I have draw or mentioned these carbohydrates in their line structures. to give you the chemistry also, so you can relate it that this is not something that which is not related to the chemistry. So this is the chemistry, and they are the compounds, but they have their biological importance and how they are working in our body systems, in our nature. So we should know their chemical structures as well. So this is a monosaccharides, and if you just see, this is the line structure. This is a carbon, 1, 2, 3, 4, 5, 6. So this is a 6 carbon structure, and they are the hydroxyl group, and this is the carbon doubly bonded oxygen. And we understood that there is the one hydrogen as well, because and now this is making aldehydic functionality, right? So as I stated in the first slide, that by definition these are the polyhydroxyl, because there is the more than one hydroxyl group, right? These are the polyhydroxyl derivatives of aldehyde or ketone. So right now this monosaccharide is an example of the aldehydic sugar, which has aldehyde as a major function, and this is the glucose. Now another one is, as I've told you, that whenever they are more moving towards the disaccharides and the oligosaccharides and polysaccharides, so they have their structural feature that they can easily cyclize under these conditions. So now this is the example of the disaccharide, and which its name is sucrose. And the sucrose is made up of the glucose and the fructose, and it is abundant in most of our fruits, and which we are taking the sugar in the form of the sucrose one. And when that digests in our body system, so that break up that bond which is between the two monosaccharides, we will talk about this bonding as well. And this is termed as the glycosidic bond, because this is between the most common is the glucose one, and our body system stored the extra carbohydrate glycogen form, so this is termed as the glycosidic bond, right? So this is basically the disaccharide structure. This is a 6-membered ring. This is of the glucose one. This is the 5-membered ring, and this is of the fructose, because the fructose is just the ketonic form of the glucose one. So in glucose, this is the aldehydic functionality, but in fructose, we have the ketone, and this is at the second carbon structure. So usually the ketonic functionality appears at the second carbon. And now the another example is the oligosaccharide, or you can say this is the trisaccharide example, because right now there are the 3 monosaccharide units which have combined together. And this is the very interesting example because it has the 3 different monosaccharides. So they could be the same monosaccharides can make a disaccharide or oligosaccharide. That could be the repetition, because cellulose is a repetition of the glucose for many numbers, and they could be the different combination. There could be the different monosaccharides repeating. So this is the combination of the glucose, galactose, and the fructose one. So here, if you just see, so there are the structural difference, because the galactose is different at the third um, carbon position, right? So from the glucose one. So in glucose, you see that if you just go back to the slide, so if you just look at this one, the first carbon has the aldehydic functionality. The second carbon, it has the hydroxyl on the right side. And the third carbon, the hydroxyl is on the left side, and the rest all are on the right side. So you should remember that the glucose has structure where the third carbon has the hydroxyl on the left side. And the galactose and mannose we will talk about in another term under the epimers. So this is the raffinose, which is the combination of the 3 monosaccharides, glucose, galactose, and the fructose one. Now, as I stated that the monosaccharides are the simple sugar, they synthesize majorly from, because our body cannot synthesize the carbohydrates, so that utilize and break down and digest and use it for its needs. So the source for the carbohydrate, the major source of the carbohydrates is basically the plant kingdom. So they do synthesize the carbohydrate by their uh, process, the photosynthesis, where they take the sunlight as a catalyst and they utilize the sunlight, water, and carbon dioxide. And from these precursors, you are getting the very complex and high carbohydrates. So if you just look at the carbon dioxide and the water, so you know that they only contain the three elements. This is the hydrogen, oxygen, and the carbon one. So monosaccharides are usually colorless. They are crystalline in structure. You have seen your table, the common sugar or your the table sugar you are using. So that is basically the carbohydrate, and you can see their crystal structures. So they are usually crystalline solids, freely available or soluble in water, but they are insoluble in non-polar solvent like the N-hexane, like the toluene. So they are not soluble in that one, but they are soluble in the polar solvent to some extent, but very highly soluble in the water. Most have sweet taste. They cannot hydrolyze further into monosaccharide units. They are classified because if they will hydrolyze, so they will or break down, so they will be um, uh, decompose into the carbon dioxide and water. So we are not getting the complete carbohydrate or the saccharide structure as such. So that's why we say that the monosaccharides are not hydrolyzed further into monosaccharide units. So there the maximum hydrolysis. So the maximum hydroxyl group we have in each of the carbohydrate, except the one carbon which has the either the ketonic or the acetyl or the aldehyde functionality. They are classified according to the chemical nature of their carbonyl group and the number of their carbon atoms. So what does it mean? So I stated that the monosaccharides, because obviously the building block is a monosaccharide, and on the basis of that we are moving towards the major classification of the carbohydrates into the oligosaccharides, disaccharides, the polysaccharides, and that classification is only the basis of the monosaccharides, which how many monosaccharides are combining to make that structure. But obviously the in-depth classification and the nature will be determined from the beginning as like the amino acid. So what kind of monosaccharide it is. So they are classified on the two ways. So the major on the functional group basis, they are classified into the two classes. So one is the aldehyde, another one is a ketone. So if you just look at this one, so this is basically the aldehydic group, right? Carbonyl, then the one terminal has one side has the hydrogen one. So this is the aldehyde side. Now this is the ketonic side because there is a carbon, and this is the carbonyl which is surrounded by the from the both side. This is the R group and this is the R group. So this has this is the carbonyl is a sandwich between the two R groups. So this is the ketone. So the if the sugar or the carbohydrate is the aldehydic, so this is called the aldose sugar. If this is having the ketonic side, so these are called the ketose sugars or the ketose carbohydrates, right? So the glucose is an example, which is a 6-carbon structure, and it has the functional group aldehyde. The fructose is the structure which has the ketonic side. So this is just the another version of the glucose, you can say fructose, with the ketone functionality. So if you just look at the rest of the structure is that all hydroxyl group are at the right side, but this third position is conserved with the fructose as well. So fructose is just the same, so you can remember that structure if you remember the glucose structure. So you just need to know that you have to put the carbonyl at the second position to make it a ketone, that the both sides are the R, and there will be no change on the third carbon. So third carbon is only different from the rest of the hydroxyl, and at the third carbon position the hydroxyl is on the left side. Now, the other is on the basis of the carbon number, as I've told you. So the smallest monosaccharides, uh, I I told that it start from the third carbon. So the simplest one is the trioses, the triose sugars. The monosaccharides which have four, five, six, or seven. So they are termed as the tetroses, pentoses, hexoses, and haptoses. So usually the most of the discussed carbohydrates are up to hexoses, and maximum so far so they are the seven carbon structures, um, carbon number structures of the carbohydrates, because chemically, if you know, so the six carbon six member cyclic structure is the more stable one. So it even go up to the seven member, but if it will be the very higher one, so that is not as stable. So in or natural sources and in a most common sources, so the most of the discovered and isolated and the extracted carbohydrates are up to the seven carbon structures. So other are the very rare. This is not the case that they don't exist. They do exist, but this is the very rare one. So most common are up to the six carbon ring structure, and we also go up to the haptoses, but not more than this, because these are not very um, readily available in nature. So if you just look at this one, so this is the Fisher projection formula where we are mentioning the each side, that which is at the right side and the left side, and the all atoms are mentioned in an open structure. So the simplest structure is a three member, and this is termed as the glyceraldehyde, right? So the carbohydrate, the simplest carbohydrate example is the glyceraldehyde, which has the one aldehydic side, and there is the hydroxyl on the next two carbons, and this is the simplest carbohydrate structure. Now there are the two versions, though we will talk about this one, that there is a D-glyceraldehyde and this is the L-glyceraldehyde. We'll talk about this in the next slide, but right now the purpose is that on the basis of the carbon, so they have categorized as the triose, tetrose, pentose, hexose, and haptose sugars, right? So here I have mentioned the table, so you can remember at least the one example for each kind of the carbohydrates with the number of the carbon. So the simplest one, the minimum number in a carbohydrate structure is the three carbon. So the example of its aldehydic structure with aldehydic functionality is glyceraldehyde, and its ketonic version is the dihydroxyacetone. Now the four carbon structure of the carbohydrate is erythrose is an example, and if there is the ketonic one, so this is termed as erythrulose. Now the five carbon structure is the ribose with the aldehyde functionality, and with the ketone functionality, this is the ribulose. So you will see that usually the ketonic functionality is having the extension of rather ulose, ulose, with as a suffix with the name to mention that this is the ketone, but there are some exceptions. So pentose ribose is also the one major component of our nucleic acids, because they are composed of the DNA and RNA, so they are composed of the ribose sugars. So one in the DNA, this is a deoxyribose, and in RNA, this is a ribose sugar, which is making the structure of these DNA and RNA or nucleic acids, which are used for the genetic and hereditary material. So the next is a hexose, which is the most common um, category of these carbohydrates, monosaccharides. So the aldehydic form, we have talked much about the glucose. So this is the aldehydic with the six carbon structure, and with the six carbon structure, but with the ketonic functionality, this is termed as the fructose. The seven carbon structure, so there is the example which is termed as the haptose, and its ketonic version is the haptulose. Now, in these structure, if we just don't be confused by this dash line bonding and the wedge line, the solid filled line, this is basically giving the idea about its stereochemistry, that either that is on the front, this is on the back. So because the carbohydrates have the chiral centers, so we'll talk about in the stereoisomerisms and what are the chiral center and how we can term that. Right now I have just given you the example with each category, that what is example of the 3-carbon aldehyde structure. So if someone asks you that name any of the carbohydrate which has the aldehyde group, and this is the 4-carbon structure, so you should know that the example is the erythrose. Or if someone asks you for the ketonic version, so you should know that this is the erythrulose. So now the stereoisomerism. So carbohydrates do exist. They have the stereoisomerism. The stereoisomerism is basically when a compound is same in connectivity, it has the same molecular weight, it has the same kind of elements. So there is only the one bond through which their spatial rearrangement can be changed. So that is the stereoisomerism. So as the carbon in the carbohydrates, they have the chiral centers, they have the chiral carbon. So a chiral carbon is that center or that carbon which is attached with the 4 different groups. So it do exist in a space that if we shift to one bond, so the whole of its angle will be changed. So there could be the one group which was on the front, so that can move into the backward. So it do affect its chemical reactivity as well, chemically. So because they do have the chiral carbons, so they do show the isomerisms, and most of these are having the enantiomers, and they have the mirror images of each other. So if you just go to the previous slide, so here you can see the glyceraldehyde, which is a 3-carbon structure. This is the aldehyde carbon, this is a central carbon, and this is a CH2OH. And if you just compare structure, so in glyceraldehyde, there is only the one chiral center, because this is a carbon which is attached with the 4 different groups. This is attached with the hydrogen, hydroxyl. This is the aldehydic side, the carbon double bond carbonyl and hydrogen. Then this is the carbon which is attached with the alcoholic side. This is a CH2OH. So only this carbon is the chiral one. So we will call that in glyceraldehyde, there is only the one chiral center. But in or other higher carbohydrates, there are more than one chiral center. So I will show you that one. So this carbon is making the 2 bonds with the oxygen, and one with the hydrogen, and one with the carbon. So that's why the one element is repeated. So this is also not having the 4 different groups, and this is a doubly bonded. So this stereochemistry, or this freely movement, is always between the single bonds, right? So they have the different groups. So when we have any element which is in a double bond with one of the elements, so you can imagine in your mind that that is attached with the same element at the 2 sides, right? So that's why this is not the chiral center. So just compare like your hands in a mirror. So this glyceraldehyde is the mirror image of each other. So if you this is not superimposable to each other, so there will be the one bond which is different from this one. So on the basis of that, they are termed as the D-glyceraldehyde and L-glyceraldehyde. This is on the polarization of light, but on the paper, how we describe or how we mention this one, that if the hydroxyl group on this chiral carbon is on the right side, so we term this as a D-glyceraldehyde. And if it is on the left side, this is L-glyceraldehyde. Now this glyceraldehyde has established as the standard or the uh, structure by which we are comparing the rest of the carbohydrates, and we termed them that either they are the D or the L1. So in glyceraldehyde, there is only one chiral center. And from this chiral center, we compare the position of the hydroxyl. If the hydroxyl is on the right side, that is the D. If it is on the left side on the chiral center, this is the L-glyceraldehyde. Now, taking this concept with you towards our next slide. So, if we are looking at the glucose, now this is the 6 carbon structure. So, what should I write and how I can judge about this, because now this is having the more than one chiral center. So which chiral center I have to compare, or I have to pick, and I have to select for assigning the configuration D or L to the glucose. So this is basically the farthest chiral carbon from this aldehydic or ketonic side. So this is the carbonyl carbon from which the most distant chiral carbon we will select, and we will compare its hydroxyl group. So if I go through this, so I wanted to show you how many chiral centers a glucose has. So this is the 1, 2, 3, and 4. So they are the 4 chiral centers in the glucose structure. So if you just compare, so which is the farthest, which is more distant from this carbonyl, this is this 4th chiral carbon, or on number basis, if we just number the chemically on the structure. So this is the carbon 1, 2, 3, 4, and 5, and this is the carbon 6. So 5th carbon, or you can say the 4th chiral center, is basically the farthest and the distant from the carbonyl carbon, and we will compare its hydroxyl position to assign a D and L configuration. So for this hydroxyl is on the right side, and if we just compare with the glyceraldehyde structure, so if the hydroxyl group is on the right side to the chiral center, so that was termed as the D-glyceraldehyde. So we will name it as a D-glucose. And if that was reverse, or this hydroxyl is on the left side, so then we can see that if the hydroxyl is on the left side, so then we will assign this glucose as a L configuration. This is the L configuration or the isomer of the glucose 1. So how you can decide that how many isomers, 3 isomers can exist in a structure. So there is a formula for it. So you have to calculate how many chiral centers the structure, the carbohydrates contain. So then you can see that what are the possible isomers it can have. So we currently we have compared, we have seen the 6 membered, which is the hexose sugar, and with the aldehyde functionality, and the example was the glucose. So we have compared that structure. So we have counted that it contained the 4 chiral centers. So the 2 power of n, which is the chiral carbons, so 4, and the net answer is a 16. So there are the 16 isomers which are possible, means that the 16 times that positions can be changed, and we can term it as a chiral possible isomers. So there could be the 8D and there could be 8L isomers of the aldose hexose sugar. So you can just switch that one, and there are the different isomers that by switching that position. So now the keto hexose sugars has only 2 power 3, and it's possible are the 8. So why this is the less than the aldo one, because in a keto, at the second carbon there will be the carbonyl, and definitely this and this carbon is no more the chiral one, and the third one was already there. So in that case there was only the 2 carbons which were not the chiral one, but now in the keto form there is a third carbon which is also not the chiral one. So that's why there is a 1 less carbon, less chiral center. So that's why the overall answer is the less by reducing the power of 2. So by this you can mention that how many possible isomers are there in a specific structure. Now we came to the epimers. This is a terminology which you should know, that what are the epimers are. So epimers are the sugars that differ, and this is only applies. So this is another version, you can say, of the isomerisms. So specifically on the carbohydrates, we use that term, which is the epimers. So the sugar that differ only by the configuration around one carbon atom are known as the epimers of one another. So the most common example is the D-glucose, D-mannose, and D-galactose are the epimers with respect to the carbon 2 and carbon 4. So you can see here, so aldose sugar has 2, 4 is equal to 8 possible isomers, and the ketohexose sugars have only 2 to 3 is equal to 8 possible isomers. So here you can see um, this is a glucose, and in the glucose we have seen that this third carbon is that kind of configuration, that this hydroxyl is on the left side, and if you just compare the rest of the two structures, so this is the fixed position, because these are the isomers, and more specifically these are the epimers of the glucose. So obviously they have to maintain the basic structure of the glucose, and rest we will see that where there is the change in their configuration and the sides of the hydroxyl group. So one is a fix, one thing is the third carbon. So I can highlight so you may understand that one easily. So I could go for the blue pen, right? So here you will see that this is the third carbon, and its structure, the orientation of the attachment of the hydroxyl group is the same as with the glucose, right? So this is just the glucose structure which is repeating. Another thing which is the same is the acetyl group, right? Aldehydic group, sorry. So this is the aldehydic, this is the aldehydic. So we will establish the concept that what would be the epimer. So we are not taking the ketonic versus the aldehyde in epimer form. So they are having the same major functionality. They have the same major skeletal structure, but where is a change? So we will see that this is now, you if you just compare it, so in the mannose structure, in mannose, you will see that this is the carbon second, where there is a shift in the hydroxyl group. So this hydroxyl, which was on the right side in the glucose, has shifted to the left. So just with this minor orientation in the spatial rearrangement, because these molecules do exist in a 3D structure, X, Y, and Z coordinates. So in that structure, if this OH has just flipped its orientation, in one case this was on the front and now it's switched back on the back side. So this is the on this side from the right to the left side. So this is another molecule which is called the mannose, and this is the epimers of the glucose, because most of the structure was the same. So there is only the one shift from this glucose. Now the third one is the galactose. This is also the epimer of the glucose, because the other change of in the structure of the carbohydrate, the glucose at the third position is the same. It preserved in the galactose. It is the aldehydic one, but the change is at the carbon 4. So here the hydroxyl, which was on the right side, has shifted to the left side. So this is the galactose. Now the another thing is that the all epimers have termed as the D-glucose, D-mannose, and D-galactose. Why it's so? Because for the D and L configuration, we have to we have to see the farthest and the distinct carbon from this carbonyl carbon. So if you just look at this one, I could use different color for this. So here you can see that this is the, here you can see, right. So if you just look at this one, this is the farthest chiral carbon from the carbonyl, and we will see that where their hydroxyl groups are. So if you just look at this one, all of these hydroxyl group are at the right side of the of the Fisher projection. So we have this stated that if the hydroxyl group is at the right side, so that will be termed in with reference to the diglyceraldehyde, because this is just resembling the diglyceraldehyde structure in which the hydroxyl is on the right side, and that is termed as the D. So this was for today about the carbohydrates, and we will talk about more about their reactions of the carbohydrates and their naming and our future lectures. So have a good time. Thank you.